a lot of this talk represents kind of my thoughts, and I've been very buried in like the theoretical use of and applications for LiDAR for a while now. So a lot of this is meant to be kind of like, Dana and I even talked about this a little bit before this, like a general overview, kind of like where LiDAR is being used, kind of how to use it, but also kind of just focus on where I think this can go, right? So my background's in ecosystem ecology and remote sensing, and socio-ecological systems are very new to me, but also very exciting. So I'm going to show you what has worked for us, particularly with like kind of a walkthrough of a big neon project that I've been on for a couple years, and then some, kind of, what's the fancy term we use now, the bleeding edge research of where LiDAR is, kind of thing. But just also meant to kind of spur conversation, spur thought. And so stop me, interrupt me anytime you want, whatever. I'm totally comfortable with that. Again, my name is Jeff Atkins. I'm coming to you from Virginia Commonwealth University. I'm a postdoc. I've been working with Chris Goff down there for about 3 or 4 years now. I came over to VCU from University of Virginia because I was really excited because we would be working in neon sites and also working with kind of novel applications of LiDAR. So we had an overview of this. I just want to kind of throw it back to you again what LiDAR really is. It's literally energy pulse, and you're measuring the distance based on speed of light. LiDAR itself stands for light detection and ranging. This may sound very familiar if you're from radar or radio detection and ranging, or sonar, sound kind of detection and ranging, right? In common, these are all active sensors, meaning they throw out their energy, they're measuring how whatever in the universe responds to that energy. That's what you're measuring back to that, in contrast to a passive sensor. I bring this up to remind you because this means that they have some tendencies that are unique to them and how they work. That is always important to consider when you're thinking about the type of LiDAR sensor that you're using, right? So going to the neon AOP, again, kind of how it works. You have two systems. One is a discrete return, one is a waveform. I'm going to show you some waveform data in a minute, which is really exciting. But discrete is, it bounces off something and gives you a signal back, right? That waveform, again, is that distributed energy. What this really looks like, and we'll go back to this, is here's a paper from 2015 from Karen Anderson and Matt Disney's group from UCL, where they're comparing the green is a waveform aerial LiDAR system, the blue is a discrete return aerial LiDAR system, and the red is what's called TLS, or terrestrial laser scanning. So to give you a sense of how terrestrial laser scanning, for the most part, is also a discrete return system. There's some nuance there, but it is a vastly higher order of magnitude of resolution, right? So per square meter, most aerial LiDAR systems are 1 to 9 points that you get. A single scan of terrestrial LiDAR can give you millions to hundreds of millions of points, which usually transfers to hundreds of thousands of points per square meter, right? So what you can see in this discrete return in the aerial system here, when they kind of go in on this, is you can see this very distinct line that kind of comes out. It's hitting a house. You get the return of the house. The TLS, on the other hand, gives you all of this information. Part of that also has to do with view angle, which is something I want to talk about, which is important to consider for aerial LiDAR as well. The TLS system sits still and scans everything around it. It'd be the equivalent if you took like a water balloon and squeezed it. The lasers are going to hit everything that we get wet, right? So if it's right there, it's going to hit Andrew, but it's not going to hit Stephanie, per se, right? Unless you move it around and then stitch everything into space, kind of mosaic together, kind of similar to what Dana was talking about with the hyperspectral. Waveform is fuzzy, is the best way to describe it. In fact, actually, when we scale up some aerial LiDAR or even some terrestrial LiDAR to make it work with some of the newer NASA sensors like JEDI, you actually have to introduce noise into the signal to make it look like waveform LiDAR. Like, it's just kind of fuzzy is the best way to describe it. And you can kind of see that in the signal, right? Because you're getting all of the energy that comes along with this. Discrete either bounces off or it doesn't, right? So you can imagine, like, if a wave pulse hits the corner of this, if it hits it directly on center, it's going to be a very hard return. But if it hits it just a little bit off, it's going to catch part of that. So it's going to change the energy ever so slightly, right? So that's kind of the best explanation I can give for that. If you compare this to like what these data actually look like different forms, you have like regular discrete return aerial LiDAR. 3D scanning LiDAR can either be stationary or mobile. It's being used a lot in driverless cars now. which is actually driving down the price of a lot of these sensors, like precipitously. There are other types of LiDAR as well. We use a 2D LiDAR, which has about a resolution of 100 points per square meter, but it's in linear meters, so it's used to profile canopies. And there's also structure from motion LiDAR, which is typically from a drone, and it works very similar to stereoscopy. Is that how you sound that? Basically, two cameras interpolating the space in between, and you can use an algorithm to drive out points from that to also get LiDAR. So the reason I bring this up is that the viewpoint of any given sensor, just like we were talking about like off nadir, really matters, and it really particularly matters for LiDAR because you want to know what it is that's in that image. So thinking about basics of how we work with LiDAR, the NEON system, and Tristan can expand on this if I say anything wrong here, there's different levels of products with this, right? Like one of the level 0 products that you can get are those raw aerial point clouds. And those are great, but sometimes you got to kind of work with it. So this is a cut up from the Great Smoky Mountains. It's just like a 10-meter wide slice of LiDAR. You get this nice little profile of the canopy. But a lot of times with the raw data, you actually have to adjust this, right? Like if I want to pull out biomass, I need to account for it. So I got to take a DEM, those digital elevation models. I got to normalize everything. There's a little bit of a startup energy that goes into that, right? Some of the other products that we spit out that we use a lot are kind of derived products, which are those canopy height models, which are already kind of nice and rectified and adjusted, and really trying to tell you the height of the forest or the height of whatever's in that system. But the general flow to any of these is you take whatever it is your raw data is that you have, you either transform it in some ways, maybe you want a specific area, so you want to clip it. If you're using a raw point cloud, you may need to do some kind of adjustment. You may want to coarsen it. The raw point clouds are pretty large data, so you do have to have some computer power to kind of get that going if you want to work with that, whereas the canopy height models and the DEM work pretty well. And then this is basically the general workflow. Like whatever you want to ask from it is like any other science question, and that kind of gets to what you ask and how you analyze it. And I usually would put in here science, but I put in here action as the outcome because there's more than just science, right? Obviously, there's application. There is policy, there's all these other things. LiDAR is really flexible in general to work with, but there's 3 kind of modes. I usually work within the open science framework, so I use a lot in the R, like the R coding language. I prefer that because one, it's free, and moving from a very large research university to a smaller research university, there was no longer the licensing to pay for like ArcGIS or for MATLAB, right? R is free, has a very large user group. Also Python, and throwing that on there for Julia as well, like other coding languages are very flexible for working with LiDAR. Also that said, LAST tools and ArcGIS work pretty good. They also have the advantage that a lot of folks in policy and government NGOs also work in that. You're going to have a broader user base. That said, they can be expensive, but I've run into the issue of working with collaborators who work in different languages or work on different platforms, and that can be an issue. One of the other things is, this is an advantage, one of the advantages of NEON and this democratization of data is having that open available data that you don't have to work with it directly from the sensor, because a lot of the sensors have proprietary software, and the actual raw data come in very strange formats that are very unique to either Leica or Regal or whichever company that they have. So if you end up, a lot of what I do is pairing the NEON AOP with other data sources. That does become an issue down the line. When I talk about challenges and limitations, is that if you have different sensors, you have to go across software formats. So you end up, the best way to do it, I think, is to just find collaborators. That way you yourself don't have to go out and learn multiple different platforms. The other advantage to open science in particular is that there's a lot of big user community. So particularly within R and Python, there are people, scientists, and otherwise like making packages, software applications to use these data. The LiDAR package, if you're not familiar with the R language, everyone who makes an R package throws R in there as some joke, right? So the LiDAR package is one that's often used in the NEON tutorials to work with LiDAR data. It's really straightforward. Another one is called R-LiDAR. That's from Carlos Silva, who's over here actually at the University of Maryland, has done really great packages. They're very well documented. There's tutorials on the NEON site that have this. University of Colorado Earth Data Science Institute wherever Leah Wasser works now, however she Earth Lab, yeah, it's got a fancy name. Yeah, something, yeah, I don't know. Great resources and super nice people that are out there to support you. So this is, a lot of like the basic to even intermediate LiDAR applications that you would want to do. There's already a framework out there. And if you're working in one of these open science frameworks, there's already extant code and people out there to support you to kind of learn to do that, right? So there's not that much of a startup energy to that. There's other packages like this. Forest Gap R was a nice one, which was trained on the tropical rainforest to basically be able to analyze forest gaps, which if you think about from a socio-ecological framework, this is a package that has a really strong application in being able to identify logging, to identify degradation, land cover change, like pretty quickly, without something that you yourself have to kind of go out and learn how to do. So there's kind of already applications in that. Part of the NEON project I worked on, we also added in there Forester or Forest R, however you prefer. We used a package, or we created a package to pair terrestrial LiDAR with aerial LiDAR to measure structure of canopies beyond just biomass or beyond forest gaps, but also kind of their arrangement and position of forest canopies. So I wanted to tell you about a little bit of what people are doing with LiDAR. And first, I was going to lead off with what started out as my postdoc as kind of like a framework for what worked for us, and also what kind of came from that. So I started in 2016 on this project with the idea we were going to use all the deciduous forest in NEON to go out and collect terrestrial LiDAR in, and to be able to use that to infer structure-function relationships of forest across the entire continent, right? So the big scale, macro scale ecology. And also, in the last year, we've added stuff with the AOP in this. So we have the entire gamut of things. So we've been talking a lot about the AOP footprints. But if you're also, I don't know if you're familiar with some of the NEON protocols, they have a lot of field data as well. So within these field data in particular, you have a lot of these distributed vegetation plots. And also, this is the Great Smoky Mountain site. There's a very tiny little red triangle you'll see. That's the flux tower. So the flux tower is a large tower. It's taking a lot of meteorological measurements. It's also measuring the exchange of carbon to and from the atmosphere. You're getting water exchange from there. It's a very high resolution, what is it, like 30 times per second or something. A lot of really good, rich data. Within the airshed of that footprint, so it's a footprint of basically everything that tower measures. For every site, there's 20 plots that are getting vegetation information measured. We were particularly interested in forest growth, so we were looking at tree diameters, right? So that's measured every couple of years. It can give you an on-the-ground measurement of how much the forest is actually growing. The tower gives you a measurement of actual carbon exchange. So two different ways to measure the productivity of a forest, either that top-down approach or from that bottom-up. So what I did was every deciduous forest that I could get access into, we went in and scanned those plots. It varied from 6 or 7 plots at some sites, just because of accessibility issues, to actually getting all of the sites in some cases. Within this, we were using a terrestrial LiDAR system like I showed you earlier that basically is attached to me. I walk through the forest. It gives you a raw point cloud. And then from that point cloud, we adjust that to give you the density of everything above it. One of the differences when talking about viewpoint between a terrestrial-based system and an aerial-based system is you think about like what they hit, right? So if you think about trees as like pizzas on the landscape, it's going to hit that outer inside, right? But if you're underneath that, you're getting kind of the inside of that canopy. So the basis for having to write a package in the first place was the fact that the raw data did not necessarily represent the forest because you have to adjust for what's called occlusion, or the water balloon exploding and not hitting the person behind you, which is based on, if you're familiar with Lambert Law, it's basically light extinction, which was developed originally to discuss the purity of beer. So to give you an idea of what the data look like, so an actual picture of a forest. Here, this is a red pine forest in northern Michigan, which is great because it grows a canopy when it's young, and then it just moves up and it keeps that canopy basically the same and creates a big open space underneath. When you actually look at the data next to it, that's what you see. You see the canopy kind of next to that forest. Those are what the data were looking like. So we used that coupled with light absorption data. So we were really interested in looking at how much light the canopy is absorbing. This is really important from an Earth system model perspective because this is kind of what drives photosynthesis. Photosynthesis, if I can talk today. So understanding better how a forest uses light, we took LiDAR from these sites, took up the entire continental gradient, It was able to show that a more complex forest is more efficient at absorbing light. This showed us that we were able to produce a model based on our LiDAR coupled with vegetation data from NEON to explain that 96% of the continental variation, which is an improvement over what used to be like a 70% explanation model based just solely on leaf area. So coupling NEON vegetation survey data with LiDAR data, vastly able to kind of improve those models based on just adding one single variable. So from that, what's been fun is thinking about, okay, now we have all this data, what can we do as we further work with NEON? So working with Bob Fahey at the University of Connecticut, we started to think, big scale, we just have LiDAR data for a forest. Can we think about forest more from like a structural aspect? Like how many ways can you build a forest, right? Like what do they actually look like? So we started like kind of throwing out these ideas while sitting by the lake. Like what does forest actually look like? There are these short and dense kind of forests. There can be multi-layered forests. They're very, very tall forests that can be open, or tall forests that can be this. So we came up with all these kind of different ideas and throw them out there. And we're like, well, we have the data. Let's actually look at that. So Bob loves PCA, so I'm going to try to explain this. If you're not familiar with them outside of community ecology, I don't like them. But the general idea is you cluster data. It spits out, these are the ones that are influential and gives you like a group. So using the NEON data, we can say, based on this, there are approximately 6 ways to build a forest in the US. You have these very low heterogeneity, high gap forests, so very gappy forest. These are the ones that actually break out. These are an Ordway Swisher. Ordway Swisher is a open pine savanna with a little bit of oak in there. And then you get these very high leaf area forests that are also very complex. Right? So these are very tall forests. They have lots of leaves, and they have lots of layers. These are like the Great Smoky Mountains, Oak Ridge. It's the Cirque site that we talk about here. Cirque is just a gigantic coastal forest, right? It's like 40-meter trees, multi-layer, very complex. And then you have some forests that kind of pop out, in the middle. Maybe they have moderate gaps, moderate complexity, or maybe they have high gaps, or they can be very uniform. So it kind of created kind of an interesting way to start to think about forests from a structural standpoint. And then, of course, my advisor had this thing for biodiversity, right? That's always ecologists are talking about how biodiversity matters. So we started to think, like, yeah, I know, right? Like we have structural data. You can obviously see which of the bias I was. This is one of my most favorite papers ever to participate in. I think it was a really great paper. But Chris was interested in like, okay, well, how do you build the complexity in the forest? Can we use the NEON data to do that? So he puts up lots of panels, but you can ignore this for the most part. Generally, the first paper we had that came out in Ecology last year was showing that structural complexity of a forest, that using LiDAR data, and both of these have AOP and ground LiDAR in them, the more complex a forest is, the more likely it is to be a higher, greater productive forest, right? Produce more forest, grow more wood, grow more leaves. And that understanding the complexity, so we have a suite of different complexity variables that come out of this, does a better job than just diversity. So if you put like diversity in there, but you also put in complexity and leaf area, complexity is the thing that drives production greater than diversity. The caveat being, of course, this is based on eastern temperate forests where the most diverse forest is like 12 species, right? But then this other really, really messy one over here is the one that's in review now. You actually have to have diversity to build complexity, but it's a step change thing. The diversity of a temperate forest, the more species you have, the more likely you are to have something that fills a niche space that builds complexity. The take home from this is like without NEON and without the AOP, this is not possible. Like it's just, there's a lot of stuff that goes in here. There's hundreds and hundreds of scans and plots. Not possible without this kind of framework. But one thing that did come out was, I lived for a long time in the Smoky Mountains, so I focus on that a lot. But in 2017, there was a series of arson fires. I think 80 or 90 fires burned down hundreds of acres of forest. We had pre-scans from those forests. So I just went back. And we took more terrestrial LiDAR scans from that. I paired it with a couple other disturbances, but in particular the Hubbard Brook ice storm experiment. Great experiment. went out with fire trucks, doused the forest, and let the ice just shred the forest. I love these manipulative experiments, as you'll see. So if you look at the bottom here, this is the Smoky Mountain forest, the NEON site. On the left and the right is post, the left is before. These little blue lines are what are called vegetation profiles. So where they stick out more, because it's moving up in height, there's more stuff there. So as you can see, the fire kills the understory, does not touch the overstory. We don't have a lot of forest fires out east, so our understanding of forest fires is predominantly driven by western fires, which typically will burn and destroy everything, right? That's just how that system works. So seeing these fires actually allowed us to use LiDAR and NEON system to show structurally, kind of how these low severity fires actually change structure. I keep hitting everything, guys, I'm really sorry. But this paper's in review now. We paired this with a bunch of other disturbance systems, some NEON, some not. But using this kind of very similar NEON framework was able to show that these low severity disturbances kind of structurally have a signature you can pick out with LiDAR, right? So this very messy diagram here at the bottom, on the left, it's showing that an ice storm decreases the amount of leaves, and a fire decreases the amount of leaves. But other disturbances, such as woolly Adelgid, or induced senescence, or beech bark, doesn't necessarily actually change the leaf area of a forest. It more changes where that occurs within the canopy. So we started getting this idea of being able to structurally describe forest a little bit more. So one of the things that has been really beneficial for us working with NEON, and it was similar to what Dana was talking about as well, is pairing AOP and NEON measurements with other things. In particular, because one of the limitations of the AOP data is it is a snapshot in time. That LiDAR that's measured in there is measured once. It's during the peak of the growing season. But if you're looking at something like a phenological transition or something that occurs rapidly in between that year, you're not going to get that signal necessarily. So NEON, in a way, is a baseline that you can kind of build off of. And that's what we've kind of done. Kind of screw with this a little bit. Part of that was being able to scale to other systems. For us, making NEON data look something like JEDI data. JEDI is a waveform LiDAR sensor that's up on the ISS right now. That's giving, not quite global, basically from southern Canada down. 25-meter footprints, LiDAR structure every couple days. But so to give you an idea of why we were focusing on this so much of pairing other data is that some of our questions, this was looking at differences in what sensors were telling us. So we have another project working at distributed plots in the Smoky Mountains, which go all the way up to 6,000 feet, so a different range of ecosystems. We find at some of these plots that there is an aerial bias, meaning the aerial sensor is actually recording something different than terrestrial sensors are giving us. So for some of these ecological applications, and this is something that's going to transfer over to SES as well, aerials, you want to be aware of what it's telling you, right? So to give you a kind of a scan in, these are different forests here, taken out, they're cut to the plot level, and half of these are hemlock forest, half of these are mixed deciduous forest, right? So we know that there's these bias that we're getting from these sensors. One of the things we can do with this is start to look at species identification in a way, which if you have something powerful like hyperspectral, you can actually pinpoint instead of looking at LiDAR and just kind of guessing at it, right? I can look at these forests and I can tell you that the hemlock forest, which is this side of the log, have no understory whatsoever because they're completely shaded out. And the other side of that log, where the deciduous are, has a predominant understory, which in my data, I see my understory in my deciduous forest, and then I don't see them in my hemlock forest, right? So these data have limitations, but that's not necessarily a bad thing. These limitations can be used for different ways. So I wanted to show you a couple other applications that people are doing with this. This is a series of other terrestrial LiDAR pinned up with aerial LiDAR from NEON to improve biomass estimations. In the forestry community, LiDAR has been synonymous with biomass. That's been the thing they've been obsessed with. Part of that is for carbon accounting, particularly areas of the tropics. We know we've been underestimating biomass by upwards of 20%. So that's when a lot of the work has been pushing on that front. neon has really kind of helped push forward this in other areas. Let's see if it stops on me now. Also, this other one, and see if this one plays. This one's from a colleague and friend of mine, Atticus Stovall, who used neon data, speaking of the California drought. I don't think it's going to play. But they paired NAPE imagery, so this kind of high-resolution ortho imagery. It's not going to show up on it. But paired with neon LiDAR to be able to identify where trees were actually dying. So they were able to identify 1.8 million trees, map that NAPE imagery over it, so basically gives you a color composite of it. They trained a model to pick out basically where red was to identify where a dead tree was, and then be able to use that neon data to map forest mortality all across California. And then waded into a huge kind of minefield, because there is apparently this debate in ecology that we weren't aware of about whether tall trees or short trees die during a drought. This data says tall trees die, but some people get very angry about that. Other work is going on. People have a lot of investment in this. Similar to Dana, we had a neon AOP fly over a site in UMBS led by Kyla Dahlin here, but her group's been working on this 4D foliar project for a couple years in neon. So using neon AOP paired with leaf sampling technology, they use a slingshot instead of the shotgun, because shotgun you can't necessarily go shoot everywhere, lo and behold. Their project's been really cool. Their Ph.D. Aaron has produced maps from neon data paired with their data to look at where canopy nitrogen is vertically in the canopy. So it was in the upper canopy or in kind of the lower canopy. LiDAR kind of gives you an ability to position that and show where that is. We've been using that data ourselves. This is my REU from this last year, who used an under canopy camera that's been tricked out to get the near-infrared signal so that you can look at greenness under the canopy. This is kind of a raw image here, and this is Evan working with the camera. And so we've been pairing that with UAV data that we're going to use to actually truth with the hyperspectral data, kind of moving forward. But this idea of like synergy, like being able to build on the neon data and really push out with these different other technologies, or even extant data. We have field data from here that goes back to like 1890, right? So we have this long-term data that we can now scale up and use to infer basically across the Great Lakes based on this camera data paired with neon data. So it's kind of a really powerful thing. We also did this on, speaking of manipulative experiments, we've been testing disturbance threshold by killing trees. So we just girdled 3,600 trees and then had a neon flyover on this. So we're going to be able to take this data that we're measuring with our students. They're measuring rapid response to disturbance, right? Like how these forests are changing, to be able to pair that with LiDAR moving forward. You can stop me at this point because I'm just going through case studies and stuff I want to talk about. But other things talking about more socio-ecological standpoint is how forest pests are changing the forest in these environments. So some colleagues of mine at the University of Boston and Harvard Forest, or University of Massachusetts, Boston, I apologize, have been looking at hemlock woolly Adelgid in Harvard Forest and kind of across New England. Adelgid is like a really interesting pest because it kind of goes up the inside of the tree and then kills it as it moves out. So Peter should be defending any time now. The only pictures I had of his data were pretty grainy from a talk that we were at in Helsinki, but we have data of our own showing this like LiDAR that he's pairing with AOP now, where it's showing like, this is the Harvard Forest cutout. The red circles indicate trees that have died from woolly Adelgid over the last, from 2010 to 2016. It takes about 4 or 5 years for it to kill a tree. So up here, like this is like posited next to Landsat. The Landsat limitation is that it doesn't necessarily pick up where the disturbance is. But when you pair it with LiDAR, so this is a LiDAR profile down here at the bottom, we can see that Landsat satellite's not working because these high mortality areas, the death is actually coming from inside the canopy. So you have this problem with a lot of optical sensors where a big green forest looks like a big green forest. But when you add LiDAR to it and some other remote sensing, you can actually see what's inside that big green forest and add information that allows you to make inferences where you were kind of limited before. We're starting to get to the point now where we can start to look at change. So LiDAR can tell us how forests are changing at like a micro scale over time. This is a group from the University of Ghent that has some pretty crazy ideas and some pretty crazy technology that I think is really something that could inform us, particularly as like neon starts to accrue data, over these time frames. We're going to be able to do change structurally that we can only even think about before. Other groups that are working on this, University of Florida, some folks are looking at doing these data challenges with neon data. Not necessarily just restricted to neon, to LiDAR, but canopy delineations using different kind of machine learning approaches to be able to give out data to the community at the individual level. And what can we do with that? We have a paper coming out in Frontiers of Ecology soon, at some point this year, maybe, led by Elizabeth LaRue at the University of Purdue, looking at how do we use neon framework, remote sensing in particular, to kind of study macroecological processes, right? So we have a case study here comparing saproot to Harvard forests, in particular looking at drought versus forest disturbance, how to understand these and start to make teleconnections. It's an entire special issue focused on this, so really excited for when that kind of comes out. Other stuff is just starting to think about what LiDAR can actually be used for that we're not doing it for right now. One of the things we've been doing is like ecological restoration. So we have, this is data I got last week from Ohio, where they had went in and removed an invasive honeysuckle that was just rampant throughout a forest. So the pre-scans showed that there was lots of honeysuckle down there at the bottom of the forest. Again, these are those vegetation profiles. And after they removed it, you get a noticeable bump over here, like you change the structure of the forest. Thinking about this big scale, we can use this data to then see maybe effectiveness of restoration or see where something is changing kind of the structure of systems beyond just forests as well. There's all kinds of crazy applications of this. People are using stuff to study lianas in forests, in the rainforest now. Not necessarily an issue in the US, but kind of interesting kind of data from that. You can, in theory, use LiDAR to differentiate leaves from wood. It works in some cases. It's a little iffy with aerial LiDAR, but there's some people out there pushing that. Because you not only get a distance, you get a measure called intensity with LiDAR that tells you how strong a return is. So there's kind of some stuff that can go along with that. We've been working on fuel load estimation as well, right? One of the byproducts of conserving and preserving land is the fact that dead wood tends to build up. A similar approach to this, like we can use and kind of use LiDAR to find where stuff is and kind of make some inferences with that, with other information about fuel load estimation. When you start to think about applications from different ways, there's some interesting stuff that can come out of this. And this one, I just wanted to show Richmond and Baltimore. This is another friend of mine's paper, where they just did urban heat island effects. So this is Richmond on the left and Baltimore on the right. So the green is like a true color image, the green being where the trees are, the white being where the not trees are. And the red is different urban heat island, different times of day. So basically, the areas that aren't trees are very red. Baltimore has the same profile. Richmond, of course, is driven by a huge history of redlining, which was a practice where you guys are probably more familiar with as most of your geographers, but basically where banks would not allow loans to people of color, limiting them from living in certain areas, which has this ecological feedback now where those systems or those particular areas of the city are less hospitable. They're more hot. They have higher health danger risk within those cities. There's a lot of uncertainty though in these areas. So if we start to think about areas where we can add, like LiDAR or other remote sensing technologies to this, we can really start to improve, these kind of estimations, understanding.
What would you improve?
Well, so those green areas, you see like all this variance here. There's a lot of variation in that. The extremes are really good to get with regular remote sensing or pictures, right? Do you think about disturbance? I can really pick up a clear cut really easily. But when you start to think about what's in the middle, like degradation, that's where these kind of other technologies can kind of come in and start to give that information.
So how would LiDAR help with the temperature measurement?
It's not. It's going to help us understand where these areas are more variable, because we can start to expand that, right? You can start to add more information and be able to describe things in a new and kind of more nuanced way. So also, like, we use it for risk management as well. Like if you live in a city that has a lot of large trees, there does become the issue about dangers of trees falling, right? LiDAR has a capability of being able to predict out which trees are more at risk of falling as well. So it does help with risk mitigation. So that's been some work with that. But I don't present that one because that one's really iffy, but it's kind of cool. Like, remember I showed you like this I forget the car with the scanning LiDAR on it now? There is one LiDAR sensor that a friend of mine in London's been using. It just kind of rotates and you ride around with your bike and just hold the thing up. And you can like map the entire structure of the street and all the trees on that. And from that, you can basically just build a model of what a dangerous looking tree looks like versus a healthy tree. And from that, you can help. Like, these are actually high risk areas. We don't have to wait till a tree falls. We can actually kind of go out there and assess, like, okay, this is a dangerous area. You got, urban forestry kind of thing on this. But so.
In case you're interested, in Baltimore, they, I don't know why they did it, but the Department of Transportation did this three-dimensional LiDAR mapping of every street in the city.
Oh, that'd be cool.
It has created a three-dimensional view of every single tree.
Yeah.
I don't understand. I saw it last week. I don't understand what's going on, but it may be something that would be of interest to you, combining with the other LiDAR assets.
One of the things that's been done in Richmond is, in Richmond we have a lot of Civil War monuments that many of us are trying to get rid of. But one of the things that's been done is down Monument Avenue is that there's been an entire 3D scan of that. And what we've done with that is it's been opened up for people for redesign purposes. Like, take these data, how would you redesign this? And so it's kind of like an open art science kind of competition. We hope that policymakers kind of learn from that. And the other aspect of it is something that could just be used for museum storage, right? Like, this is what Monument Avenue used to be like. LiDAR has a lot of strange applications. Like, it's been used in forensic science a lot lately. One of the big industries is if there's a car accident, they will call out people with LiDAR, come out there and scan a scene, and you can do accident reconstruction. It's been done for murder scenes. You can go in there and scan LiDAR. The LiDAR doesn't lie, right, or whatever. It has a lot of weird applications. And so, like I said, I come from this from like a very ecological standpoint, but also we've been really trying to push it and make it do things that it wasn't meant to do. And that makes me kind of always open to different things. So this was just me kind of thinking out, like, what are the kind of limitations but also challenges of this. One of the issues we have with scaling is that we have neon footprints, but there are other LiDAR sources that kind of came up the other day when we were talking this one, when Tristan was talking. There's sources like Open Topography or USGS. Some states like North Carolina and Indiana have full scans of the entire state. So for scaling purposes, there are some other additional data that are out there. Additional remote sensing technologies, maybe optical measures like MODIS or Landsat, but there's stuff like ICESat, which is basically radar, that kind of has a similar signal to it as well that can be used for that. A lot of my work focuses on this mesoscale, right? Being able to bridge using the terrestrial LiDAR or something like Internet of Things, sensors arrays, to be able to build up additional auxiliary data to make ecological functional predictions or forecasts or even kind of inference from that. We have the temporality. It's an issue, right? Like, it is kind of a snapshot in time, but it's something to think about. And there is like a human aspect to this. There's some skills that need to be built, computationally, theoretically, to be able to understand and work with the data. And part of that can be time intensive. You have to kind of make a decision. Like, is it worth it to be able to invest in this, to be able to learn it, or is it something I can do through collaborations? That said, like, my thing that I've always been big on NEON and other sensor networks is democratization of data, right? I can't buy an airplane, but they can, and they give out that data. So you also think about like smaller universities or smaller cities, like people who don't have huge research budgets. This data are free and available. I think that's why I've also pushed things like R and Python as learning to work with these data, because they don't cost anything. It's just time and effort. But there's, of course, funding. You got to pay people. And that's kind of our biggest, I think, limitation. Like, when we said that yesterday, that was the first thing I thought of. Was like, well, somebody's got to pay me to work with these data, right? Like, you got to pay students. You got to pay researchers. You have to pay your own time. You can't just do everything for free. So that's really all I got. This is kind of my last closing thought, was that, I particularly work in forest, and forests aren't really restricted to just being natural, right? They represent our values as a society. The areas that we choose to preserve are areas we chose to preserve for a reason. And that said, like, they always represent some kind of management. But like, broadly, you can think of this, really, that's ecosystems in general, right? Like, our oceans look like our ocean landscapes because that's kind of what we've chosen to do, whether it was intentional or not. And I think remote sensing, broadly, why I became interested in it, is it's a way to look at that. The way that you choose to look at it is different, right? Like whether it's through a satellite or through LiDAR or hyperspectral, but it still kind of is a way of looking at the environment to understand how we got there. So with that, that's my random thoughts on this, and I'm glad to help in any way clarify anything that was me being too confusing. So.
Any questions?
Yeah.
So you and Dr. Sankey were sitting by the lake thinking about different types of forests, and of course, Neon has kind of a smattering of sites across the eastern United States. What do you think we're not capturing well that would have popped up in that two-dimensional PCA clustering plot?
So
How do you think that relates to challenges in terms of scaling between our sites?
yeah, so one of the things that really, I talked about leaf area a little bit. Leaf area, when you measure from a forest, is literally just the amount of leaves that you have there. If you look at that across the US, it's a nice linear relationship. When you start to think about how those are arranged in space and start to consider the complexity of forest, it's a nonlinear relationship. So you have these really complex forests, you have these kind of in the middle, and then there's this big gap down till you get something like Ordway, those open savannas. So Neon allowed us to fill out what that looked like, but we had this big gap in the middle. And that became the open question, was like, okay, is that an open gap because it's not being captured by Neon, or is that an open gap because you functionally, structurally cannot build a forest that looks like that, right? Like if you think of the, a random arrangement of you're filling out a square of like, this looks like this looks like this, like can you have a low complexity, moderate biomass forest, or whatever you arrange that, like that's an open question.
Well, managers in Pennsylvania are suggesting that it's because of the history of land use, and those forests are underrepresented because we haven't managed for them.
Yeah, I mean it's true. It's like from a structural standpoint, it is an open question. And if Neon is mostly focusing in, quote natural areas, right, and not highly managed areas, we don't know if that exists. Like we've done, I had a student for a couple of years go off and do managed forest, like look at managed pine stands in particular, to try to fill in that gap, and they don't fill in the gap. So yeah, I think it's an open question, but yeah.
I think one of the, you asked a structural question, and so deer weren't in Maryland in 1930, and in our field plots we can see when the deer entered those forests.
Oh yeah, yeah.
And it'd be one of the things you could look at is what is the impact of deer on biomass and structure.
Yeah, absolutely.
They're just like a big lawnmower.
Oh yeah.
But then we also have like coyotes starting to come into Maryland now, and hopefully the coyote are going to take out the little deer. And truncate the pyramid
Yeah.
of deer, and then you can see like how does like the coyotes then affect the forest structure. So there's some underlying ecological interactions that are manifest in the structure that would be really interesting to be able to see.
We have, it was buried in one of these plots, but there's a Furno experimental forest in West Virginia, has a long-term acidification experiment. So they've basically been just dumping nitrogen on this forest for 30 years, like since 1989. And the idea was to mimic like the absolute ridiculous acid rain load, right? And so when you scan those forests, the forests that have the amendment are taller, but there's no understory, which makes sense. Tree grows tall and like it shades everything out, right? There's always that vertical competition aspect of it. And whereas the standard forest, which to be fair, like have that observation effect, they also have the background effect of nitrogen. So they're getting a ridiculous amount of nitrogen because the mountains in West Virginia are right from the exposure from the Ohio Valley. They have an understory. So yeah, you get these like weird effects. Like the Smithsonian site adjacent to Neon has a long-term deer exclusion experiment. We have one in Michigan as well, and we see the same thing. You exclude deer, you get an understory. If you have deer, you don't. So.
That makes me think of another potential application of the context of human health with Lyme disease, if there's any way to look at relationships between forest structure and wildlife behavior and proximity to people in terms of kind of density of risk for Lyme disease based on species that would tend to carry those ticks and things like that. I don't know, it just seems like there's applications for thinking about connections.
The coolest work I've seen is Danielle Rappaport at Maryland has been doing terrestrial and aerial LiDAR to look at like bird biodiversity by pairing the LiDAR with ecoacoustic data. So being able to like record bird songs, use like statistical techniques to pick out like, from the bird song data, or that audio data rather, like this is how many birds this is because of the unique sound profiles of birds, and be able to show.
And they're connecting that with the forest.
Yeah, she's able to connect that with like forest structure and show like a more complex forest is more intact, but also means you have more space for birds, right? Because like in ecological theory is this idea of niche space. Basically, if you have a more complex forest, in theory, there should be more niches, right? There's a saturation component where if you have too many niches and each niche is too small though, right? So whatever, but yeah. Danielle Rappaport is at Maryland, so.
Dr. Rappaport.
Dr. Rappaport, yeah,
As
she's.
of like 2 weeks ago.
Nice, okay, yeah. So she's presenting in my session at ESA this year, so if you're in Salt Lake, please come. So. Cool, all right, yeah, thank you.
Thank you.